Imagine two particles, as tiny as you can imagine, linked together in a way that seems to defy common sense. This is the essence of quantum entanglement, one of the most bizarre and fascinating phenomena in the quantum world. When two particles become entangled, their fates become intertwined, no matter how far apart they may be. Imagine separating these entangled particles, sending one to a laboratory on Earth and the other to a spaceship hurtling towards the Andromeda galaxy. If you were to measure the state of the particle here on Earth, you would instantly know the state of its entangled partner, millions of light years away. This instantaneous connection is what makes entanglement so strange and so captivating. It challenges our everyday understanding of how the world works, where information seems to have a speed limit imposed by the speed of light. Entanglement doesn't just tell us about the weirdness of the subatomic world, it also opens up incredible possibilities for new technologies. Quantum computers, ultra-secure communication networks, and even teleportation are all being explored as potential applications of this mind-bending phenomenon. To understand entanglement, we need to delve into the heart of quantum mechanics, the theory that governs the behavior of matter at the atomic and subatomic levels. In the quantum world, particles don't behave like tiny billiard balls. Instead, they exist in a haze of probability, their properties undefined until measured. When two particles become entangled, their properties become correlated. Imagine flipping two coins that are linked together. If one lands on heads, you know instantly that the other must land on tails. Entangled particles are similar. Their properties are linked, even if we don't know what those properties are until we measure them. This connection isn't just a matter of shared history. It's as if the two particles are constantly communicating with each other, no matter how far apart they are. If you measure the spin of one entangled particle and find it to be spinning up, the spin of its partner will instantly flip to spinning down, even if it's on the other side of the universe. This instantaneous connection is what Einstein famously called spooky action at a distance. He was troubled by the idea that something could influence something else faster than the speed of light, which he believed to be the ultimate speed limit in the universe. Einstein's theory of special relativity, published in 1905, revolutionized our understanding of space and time. One of its central tenets is that nothing can travel faster than light. This speed limit is not just a theoretical curiosity, it's woven into the very fabric of space-time, affecting how we experience time, mass, and energy. Entanglement, with its apparent instantaneous connections, seemed to directly challenge this fundamental principle. How could two particles communicate with each other faster than light, without violating the very laws of physics? Einstein believed that entanglement must be explained by some hidden variables, some yet unknown properties of the particles that predetermined their states. He argued that the particles weren't really communicating instantly, instead they were carrying with them hidden instructions that determined the outcome of any measurement. This idea, known as local realism, suggested that the strangeness of entanglement was just an illusion, a consequence of our incomplete understanding of the quantum world. However, experiments in the latter half of the 20th century would prove Einstein wrong. Entanglement is real, and it does involve some kind of non-local connection that defies our classical intuitions. In 1964, physicist John Bell devised a way to test whether Einstein's idea of local realism could explain the strange correlations observed in entanglement. Bell's theorem, as it came to be known, proposed an experiment that could distinguish between the predictions of local realism and those of quantum mechanics. Bell showed that if local realism were true, there would be a limit to the correlations that could be observed between entangled particles. However, quantum mechanics predicted that these correlations could be stronger than local realism would allow. In the 1980s, Alain Aspect and his team at the University of Paris conducted groundbreaking experiments that put Bell's theorem to the test. They generated pairs of entangled photons and sent them to two detectors several meters apart. The results were astonishing. The correlations between the photons were stronger than Bell's inequality allowed, violating local realism and confirming the predictions of quantum mechanics. These experiments, and many others that followed, provided convincing evidence that quantum entanglement is indeed a real phenomenon, and that it involves some kind of non-local connection that cannot be explained by classical physics. The spooky action at a distance that Einstein found so unsettling was here to stay. While entanglement allows for an instantaneous connection between particles, it's important to understand that this connection cannot be used to send information faster than light. The reason for this lies in the probabilistic nature of quantum mechanics. When you measure the state of an entangled particle, you are not actively choosing the outcome. Instead, the outcome is determined randomly, according to the probabilities dictated by quantum mechanics. The instantaneous change in the state of the other entangled particle is also random. This randomness means that you cannot control the information that is seemingly transmitted between the particles. It's like trying to send a message using two coins that are flipping randomly. Even though the coins are linked, you can't force them to land on a specific side, so you can't send a meaningful message. Imagine trying to send a message to your friend on the spaceship near Andromeda. You might agree beforehand that if you measure spin up it means yes, and spin down means no. However, you have no way of forcing your particle to be spin up or spin down when you measure it. The outcome is random. Your friend will see a random sequence of yes and no signals, with no way of knowing if you're actually trying to send a message. So, while entanglement is a fascinating and very real phenomenon, it doesn't violate Einstein's theory of relativity. Information still cannot travel faster than light, even in the bizarre world of quantum mechanics. Despite its inability to send information faster than light, entanglement has enormous potential for revolutionizing technology. Scientists and engineers are hard at work exploring how this bizarre quantum phenomenon can be harnessed to create new and powerful devices. Quantum computing entanglement lies at the heart of quantum computing, a revolutionary approach to computation that promises to solve problems currently intractable for even the most powerful classical computers. Quantum computers exploit the superposition and entanglement of quantum bits, or qubits, to perform operations that are impossible for classical computers. This could lead to breakthroughs in drug discovery, material science, artificial intelligence, and many other fields. Quantum cryptography entanglement offers a way to create ultra-secure communication channels that are impossible to eavesdrop on. Quantum cryptography exploits the fact that any attempt to intercept entangled particles will inevitably disturb their state, alerting the communicating parties to the intrusion. This could revolutionize secure communication, protecting sensitive data from hackers and cyber attacks. Quantum teleportation. While it sounds like science fiction, quantum teleportation is a real phenomenon that has been demonstrated in laboratories around the world. It involves transferring the quantum state of one particle to another particle, even if they are separated by a large distance. This isn't teleportation in the Star Trek sense. No physical matter is transported. Instead, it's the information about the particle's state that is transferred. These are just a few examples of the many potential applications of entanglement. As our understanding of this remarkable phenomenon grows, so too will our ability to harness its power to create technologies that were once considered the stuff of science fiction. Quantum entanglement doesn't just challenge our technological abilities, it also forces us to confront profound philosophical questions about the nature of reality, locality, and the fundamental connectedness of the universe. The idea that two particles can be linked across vast distances, their fates intertwined in a way that transcends our everyday experience, raises questions about the nature of space and time. Is there more to the fabric of the universe than we can perceive with our senses? Entanglement also challenges our notion of individuality. If particles can be so deeply connected, does this interconnectedness extend to larger systems, even to ourselves? Could it be that we are all part of a vast interconnected web of existence, linked in ways we are only beginning to understand? These are questions that philosophers and physicists alike are grappling with. Entanglement forces us to expand our view of reality, to consider possibilities that lie beyond the realm of classical physics. While we may not have all the answers yet, exploring these questions can lead us to a deeper understanding of the universe and our place within it.